All right, welcome AP students to your AP Unit 7 pre-lecture on chemical equilibrium and reversible reactions. We have just finished up Unit 6 on thermodynamics, where we looked at how energy, enthalpy, and heat all work together to explain certain phenomena regarding chemical processes in the exchange of heat flow, as well as the transformations of energy in general. And now we're going to take a look into how do we know where a reaction is at? And particularly for a reversible reaction, a reaction that can undo itself, where do we see the reaction find its kind of balance, its preferred state between forward versus reverse? So first and foremost, let's quickly define something. So a reversible reaction is a reaction that can form both product, we call that the forward direction, and reactants, we call that reverse direction. All right. So a lot of reactions can be reversible. So like one of the best examples of reversible reactions are actually a synthesis and decomposition coupled reaction. So one direction we would call synthesis, the forward, the undoing of it we call decomposition, right? And of course, we have physical state changes. So it doesn't always have to be a chemical process. Like we can go from solid to liquid, and we can go from liquid to gas, and we can go the other way around, okay? So now let's look at why we need to know this. So in the bigger scheme of things in chemistry, we care about a term called chemical equilibrium. And chemical equilibrium is actually more of a status. It's a term that defines a status. So the status is that equilibrium is when the reaction, okay, when reaction achieves equilibrium, okay, the rate of the forward reaction, so the kinetic rate, right, the rate of reaction, the kinetic speed at which we are forming product, okay, is equal to the rate, the kinetic speed at which we are undoing or forming reactant, rate of reverse. All right. And a couple of things that you should realize is that one of the best way that we can tell if a reaction has reached the status of chemical equilibrium is that the total concentrations of product and reactant stay constant. All right. That's a really good indicator that you've reached equilibrium, because if you already know that this is reversible, and this is of course assuming that you know you're working with a reversible reaction, okay? And you see that as a reaction runs, your product and reactant concentration aren't changing, but you know that the forward and reverse are happening still, they're dynamically still actively happening. That means that you know you reach equilibrium because the rate of the forward, the rate of production is equal to the rate of reverse, the rate of undoing, and therefore your net change in concentration is nothing. All right. Another great way to know if you're in chemical equilibrium is we say that, actually, no, that's actually the main way. Sorry, that's the main way. I'll get into other ways in a little bit. But one other thing you should know about chemical equilibrium is that the rate of consumption or like use of reactant is still, right, everything related stoichiometrically to rate of production. Okay. So that's just a reminder that all of the previous ways that we've connected product and reactant don't disappear in this, right? So that is probably a given, but I have to say it. And so let's just kind of quickly look at a couple example problems of how we can use rate to predict amount being formed or being consumed. So in a reversible reaction. So what we have here is NO2 is being consumed at a rate of 0.031 moles per second in the equilibrium, so reversible reaction below. How many moles of N2O4 are being consumed each second? So I know that for every 0.031 moles per second, NO2 is being consumed, which means that, okay, according to our chemical reaction, for every one N2O4, I consume 2 NO2. So therefore, at equilibrium, I am also producing at the same time a rate of 0.016 moles per second of N2O4 is produced. And if you're like, doesn't this just seem like kinetics? Yeah, it is. And what we're saying is that now we're not just talking about kinetics forward, but we're also talking about kinetics backward. Two kinetic directions happening at the same time, right? But a lot of the mathematical principles so far are very familiar. Okay, so this next one, SO2 and O2 are placed in a sealed flask where they can react to produce SO3. When equilibrium is achieved, therefore the rate of the forward is equal to the rate of the reverse, is being produced at a rate of 0.0082 moles per second. How many moles of SO3 are being consumed each second? So if I know that I am producing, and one second, I don't know why my pen is so crazy. Okay, so if I know I am producing, okay, SO3 at a rate of 0.0082 moles per second, and I am in equilibrium, or I have achieved equilibrium. Therefore, I know that the rate of the reverse is going to be equal. So therefore, I am also consuming 0.0082 moles per second of product. As soon as I make it, I'm undoing it, okay? 2, how many moles of O2 are being produced each second? Well, I know that for every 0.00, oops, and I want to be in black, for every 0.0082 moles per second of SO3 being produced, okay, I know that actually for SO3 being consumed, so I'm basing it off of the previous question, consumed, I know that I'm going to produce in the reverse direction 1 O2 for every 2 SO3. And that would mean I would get a 0.0041 mole per second of O2 being produced in the reverse direction at this given rate. Okay, in equilibrium or at equilibrium. So then how many grams of O2 are being consumed each second? Well, I know that if I am producing O2, then I am also consuming at that rate of O2. Again, at equilibrium. This is really key. We're going to talk about problems where we're not at equilibrium, so we can't quite make all these assumptions, but right now we're at equilibrium. We are at the point when the rate of the forward is equal to the rate of the reverse. The rate of forward is equal to rate of reverse, okay? So if I know that I am producing 0.0041 moles per second of O2, I'm consuming that. And I just need to simply go from moles to grams per second. So I would use my molar mass of 32 grams for every 1 mole, of O2. And I would get, I am consuming 0.13 grams per second of O2. So as you can tell, chemistry tends to work with what we call dynamic equilibrium or dynamic equilibria, where we are actively reacting in forward and reverse direction. Physics is more of a static equilibrium problem set where you have two forces that are just held constant. So just to kind of offer you just a little bit of a differentiation between chemistry and physics in this area. So there are more ways to recognize. Of course, the number one way to recognize is what I mentioned earlier, constant reactant and product concentration for when a reaction has obtained equilibrium. But we could also measure it through other properties that are indicative of concentration. So you could look at the color, especially if the color has to do with pH, right? You could look at temperature if that was connected to your reaction, exo versus endothermic. You could look at gas pressure, right? And when I say temperature, usually what I mean is have you reached thermal equilibrium? Okay. Gas pressure, we have always used as an indicator of the concentration of gaseous particles present. When looking at an open versus closed system, when a reaction is in a closed system where there is no exchange of matter, and preferably an insulated closed system where there's no exchange of heat, right? What you would see is that you could look at simply the mass, right? And since you know you're not losing any in a closed system, you can look at the mass, and that could be an indicator of whether equilibrium has been reached. All right. Is the mass not changing at, well, ooh, that's actually a little hard. I guess you could say, especially, let's put it this way. You could look at mass if it was a heterogeneous system. What you could do is you could, in a closed system, you could look at mass versus pressure. If you're going from a solid to a gas, stuff like that. But ooh, that's a little bit of a, yeah. Okay, let's just move on. That's, you kind of get the idea along that way. And then if it's an open system, what we say is that your properties would have to be a little bit more loosely measured, and it's more of an approximation. So you would say is that they appear to be in a steady state or constant condition. And so when trying to determine equilibrium, we definitely as chemists prefer the closed system for or conducting equilibrium equilibrium-based reactions in a closed system, because that's easier for us to identify the following. This is a little bit harder, open systems. All right. So a third thing to consider when trying to recognize if a reaction has obtained chemical equilibrium is that when a reaction and I'm just going to actually shorthand this. When a reaction, all right, has a stress or change applied, so like added concentration, change in external pressure, which causes the system's pressure to change, right? When a reaction has a stress or change applied, what we see is the reaction will actually shift its equilibrium. Will shift its equilibrium position in a way that restores equilibrium. So you can kind of think of it like a balance beam, right? Before we are completely in equilibrium, during some force is applied, right? Maybe we have some force applied, all right? And that's going to create a heavy weight on or an unbalanced, right, status. And so what's going to happen is that our reaction is going to respond in such a way that it wants to return equilibrium. So what we might have to do is we might have to shift the position of our equilibrium in order, all right, sorry, in order to pull back up that side. If we're looking at like a balance beam, pull back up that side that has been dropped down, has been affected by this original stress or change, right? So let me quickly label this as before, during, after. So before, we're at equilibrium. During, we have a stress actively occurring. And after, what we see is we see a response that establishes new equilibrium. Okay, so how exactly does equilibrium get established? Well, what we see is, okay, the rate of the forward, for example, this might be an example, the rate of the forward slows down over time, allowing, and possibly time, and the rate of the reverse speeds up, allowing, okay, the consumption of excess product, right? So let's say, yeah. So let's say you had more product added, kind of like in the picture on the right side where the product, we conventionally read left to right product. We add more product, hence imaged by that addition of the purple block. That's going to create an imbalance. The reversible reaction doesn't want to stay in balance. So what will happen? It will have the rate of the forward slow down. So the rate of the reverse can speed up and consume that product. Therefore, kind of alleviating the stress of that additional product, imaged by the blue arrow going up, kind of the alleviation of that pressure. And then, of course, the shift of the new fulcrum. Now we have a different rate forward equals rate reverse kind of moment where balance is established, okay? So, and then there's a graphic right to the side if that is a graphic that you prefer, all right? So go ahead and do the following checking questions, pause me, and then I'll reveal the answers. All right, so hopefully you guys took a moment to quickly check. The first one is false. The reactant concentration always equals the product concentration at equilibrium. No, all we care about is that they stay constant, but not that they are necessarily equal to one another. Because remember, stoichiometrically speaking, it might be totally different, right? When approaching equilibrium, reactants decrease while the product increases. That is true with regards to, okay, the example above. And I should actually put that note that this is referring to the example above. Example situation above. Okay. And the concentration of the reactants holds steady at equilibrium. That is also true. It's one of the best ways we can identify whether equilibrium has been reached for a reversible reaction. And before achieving equilibrium, the rate of the forward is less than the rate of the reverse, again, referring to the example above, and that is false, okay? And you can see that in the graphic here, that the rate of the forward is, the rate of the forward is in an upward trajectory at the beginning. So, great. Good job, guys. Tomorrow, we're going to talk about Le Chatelier's principle, the principle that we use to help us determine how a reaction will shift depending on the different types of stresses that it can be exposed to. All right, guys. Good job.